back to me. Okay, so here we go. All right, so for the first one, I'm thinking 33, and no, 33 was the more challenging one. How do we do on number one? I mean, sorry, 29. You utilize the coefficients, you use the coefficients to help establish the rate as it pertains to like the whole entire reaction as a whole. But just be comfortable with seeing like change in concentration over change in time. So that was the chlorine, diatomic chlorine. They told you that it disappeared at 0.012 molar per second. So to relate that to the fluorine and then the chlorine trifluoride, you just have to adjust the ratios as it pertains as 1 over the coefficient. So each of these 1, 3, and 2 were utilized, and it gave you the exact concentration change. Hold on, smartboard's not smart right now. Usually that works. Okay. All right, so then as you address the fluorine, it has a coefficients. You'll do that as 1 over 3 as it relates to the chlorine, since it's a 1 to 3 ratio, so there's no other coefficient here involved. So as you saw for the consumption of fluorine, it's 0.036, so it's 3 times as high. And then separately, as this is challenging today, okay. Separately, as you saw for chlorine trifluoride, it's being produced at a rate of 2 times the amount of chlorine it's consuming, so it's twice as much, so it's 0.024 molar per second. Thumbs up? Okay, so for the average rate, and your values might be slightly different than mine, or even slightly different than the textbook, just because it does depend on how accurate you are looking at that tiny graph, so your values might be here different, but understand the process and we're good to go. So if you're ever finding the average rate and it gives you a span of time, you have to use that as your span of time. So T2 is our 25 seconds, and then T1 was our 0 seconds. So that's 25 minus 0 on the bottom. And then the rate is always concentration change over time, so we're looking for the concentration at those independent times. So at 25 seconds, it was 0.75 molar. At the 0 seconds, it was 1 molar. So it gives you a 0.25 over 25, so it should give you 0.01 molar per second, but then you do adjust the negative because you're not talking, and negative rates are always expressed as positives. Thumbs up if you can do average. All right, some of you guys are correcting your papers, good. Make sure you note this, because this is the stuff that we won't review for a while, the graphical analysis side of things. We do have another problem set, but it's a little easier. So then part 2 is the instantaneous rate at 25 seconds, so you have to put a dot on the 25 seconds, right here, and then make a tangent. And it really does depend on how steeply sloped or not so sloped your tangent is. But if you try to get it as close as you can, you should end up with approximately this. So it was really close to your average because there wasn't too much of a slope change over the course of that time. But you do y2 minus y1 over x2 minus x1. So I did try to choose as close as I could. So I did 0.6 minus 0.89, and then 40 minus 10. So you got approximately 0.009667. I mean, it's approximate. So what points did you guys choose? Fatima? Say again? 0.95 and 0.4. Those are your concentrations? Okay. So you took your tangent way high. Okay.
I do like my tangent, and I made it like go all the way down to the x and all the way to the y, and then divided it into values. I got around the same.
You got around the same?
Yes.
All right, because that's gonna hit. That's a perfect way to do it. I usually draw my tangent really as short as I can get it, and then try to line it up with the time. So I lined mine up with 40 and 10, so that it was kind of splitting the 25. So I think that's a more effective way to do it. Megan? So we're speaking to how the graph represents concentration versus time. I had a graph like this, right? On 33. So at 25 seconds, you had to pinpoint where that was on the graph. But then you have to draw a tangent line to an instantaneous rate. You have to go at that time and draw a tangent line to that point. And that tangent line is what you're finding the rate width. So I kind of figured out what it was here. So I think that was my 10 seconds. And then what it was here, which is my 40 seconds. And I did those 2 points and I found the rate as it pertains to concentration versus time. Okay. Major questions on finding tangents. Minor questions on finding tangents. Yeah.
So the 25 seconds, is that looking good from that one?
I try to make mine midpoint so that's still approximate, but like I said, it's kind of like JT dishes all the way across the board from axes to axes, or you can do it as a short line as you want to, but as long as you can kind of estimate what concentrations those fall with, you're good to go. Truly, it shouldn't matter. We should all get approximately actually what this is, but my exact was 0.009667. Okay, we'll work with that some more. All right, so the rest of this, what was this next one? Oh, at 50 seconds, okay. So you had a instantaneous rate law again, or rate question again at 50 seconds. Take the point at 50 seconds, wherever that was. You should realize though, is it as steep or is it more shallow? I don't know if that's the right word, shallow of a slope. So what should the rate be, higher or lower? Lower, so it should change less in concentration over that time. So as you calculate at the 50 seconds, still consumption of bromine, I did 70 seconds and 20 seconds as my two. I got 0.0068 molar per second, and to me that made sense because I knew that it was supposed to be lower, so it was lower than my last one, so I was good to go. So thumbs up on the process for tangents once again. What was different about this one? It was just less, right? I mean, it's just you're finding the tangent once again, okay? And then to compare that to the production of hydrobromic acid, which was HBr, or hydrogen bromine gas, bromide gas, the ratio, I don't have the balance chemical equation on my paper here, but the ratio was a production of 2 for the consumption of 1. So you should multiply the rate by 2 to show how you're producing something at twice the rate. So that was going to be 0.0136 molar per second. So the incorporation of that 2, did you guys pick that up? Okay, you probably want to write, some of you guys are shaking your heads, I hope you're writing some of this down. I don't know how you absorb stuff. Okay. So all the graphs we've seen thus far have been like this because they're showing the consumption. So they're showing how reactants react and they're decreasing over time. But what happens to products over time? They're increasing over time. So eventually, I mean, we're going to put the graphs together. We're going to put reactants going down and products going up. So that's going to be equilibrium in our next unit. But for the time being, if you just separately sketch your production of products, it does have to be positive, but you do have to have it going twice as high, so twice the slope over time. So that's why they always ask for a rough sketch, because it doesn't technically have to be perfect, it just has to be relative. Okay, we will work with some of this more. I knew I needed to go over 33. What else do I need to go over? Yeah. Slope from, so this was the HBr concentration, right? So I'm doubling the bromine, so Br2's rate of consumption. So I went from, don't have the other graph in front of me, but it looks like that on the board. So whatever the consumption from 1 molar to 0.3 molar, that time difference was, I don't have that right here in front of me, but bromine should be producing at twice that rate. So this consumed 0.7 molar, so this should be producing at 1.4 molar. In that same amount of time, so I guess it was 100 seconds. So that's how I kind of gauged my slope. So I made it produce 1.4 moles per liter at 100 seconds. Okay. All right. I think the last two were easier. Can I hold off on this for a second? Okay. So let's do integrated rate law. I'm going to talk about some of the math behind it, but I'll specifically tell you what you need to write down. Okay. So some of you guys are going to be thrilled with the math, and some less so. Before we move on, I just want to remind you what we actually know. Okay, so we already know there are a lot of factors that can influence rate. Give me 1%. Temperature, what else, Marcus? So surface area now. Okay, so the size of the container. Okay, you're like trying to say the density of it. So how close the particles are to each other in reference to volume. Qui, inclusion of catalyst, and one more, everybody. Concentration, right? So there are a lot of factors that can influence the rate of reaction. Specifically, we've been referencing what when we're talking about table logic? Concentration, because that's what we've been focusing on to see how that impacts the rate of reaction. So I did say exclusion of zero order because technically zero order does not have concentration as an influencer of rate because it's not important to the rate of reaction. We know that we can express rate in two ways right now. Changing concentration over changing time from a graphical analysis standpoint, or as a rate law, our rate is equal to K concentration of some reactant. So we're feeling okay with those. Okay, we're going to have one more way to express the same exact thing, but with reference to time. Okay, so as a quick reminder, math, right? Math does become pretty important here. All right, so we always talk about correlation. We always talk about correlation between variables. What factors do we always consider as we look at the correlation? If we want to see if variables have a strong relationship. R squared value, right? So R squared gives us this called the correlation constant for a reason, right? So what number would indicate that it has a strong correlation? 1, right? But do we ever have exactly 1? It's usually what? Like 0.999 and some change. So we're looking at R squared a lot today. So have your calculators out. We're going to graph some stuff and I'm using our stat plots. The value that a value at like 0.999 means that there's a linear relationship between those two variables. So we have been looking at concentration versus time, but I can manipulate, we will be looking, no we haven't. Okay, we have been looking at concentration versus time, but what we can start to do is we can manipulate concentration. So if this is an R squared of close to 1, then we would say that concentration versus time is a linear relationship, yes? Okay, if that's not close to 1, I can manipulate concentration. Think way back to our blue food coloring drink Gatorade lab, and I had like one group do different variations. Do you guys remember that? Does anybody remember how we varied our data? Say again? One more time? Well, we varied how we input this in the calculator. I think we had absorbance, and I had you guys, or transmittance. You guys had transmittance. Someone said negative log. Okay, so we're actually going to do natural log, but we're going to vary it as ln of the concentration versus time. Okay, we're going to see what the R squared value is, and then there's one more. This was in your reading too. I'm just seeing what you remember. Anybody? 1 over the concentration versus time. And we'll look at the R squared value. Okay, so we're basically going to vary the concentrations. We're going to look at the data we have, and we're going to look for the linearity between variables. If it's linear as this, with this method, it's one order. If it's linear in this method, it's another order. If it's linear in this method, it's another order. So we have 0, first, and second order. We're going to see which one it correlates with, and then that will be our next and newest rate law. Okay, so right now you're like, what is she talking about? But we'll make more sense of it shortly. All right. Okay, so I'm going to be writing along the board, so make sure you kind of keep up with me here. Do I have some of this printed for you? I'd love to ask that question. Cassie's got the one paper eventually I'll use. This one, I did copy it big. Eventually we'll get there, but I'm not quite there yet. Alright, so the integrated rate law just basically means as it integrates with time. So that's really our newest factor that we're considering now. We are going to keep it simple. A lot of times our rate laws that we've been using have had 2 and 3 reactants. We found all the orders of all those reactants, right? So it gets pretty messy when you have more than one reactant with integrated rate laws. So we usually try to keep it simple. I will always ask for a single reactant. I will not ask for you to find the integrated rate law for anything with 2 reactants or 3 reactants. And technically, once we know the differential rate law, we immediately already know the integrated rate law because it depends on the order of that single reactant. So once we know one, we already know the other. It's just you guys don't know what the other one, how to write them yet. That's what we're learning today. this is just introduction and kind of showing how we're looking at differential as it compares to integrated. So if I give you concentration versus rate data, if I give you that kind of data, what type of law can you immediately find from that? Differential rate law, or just a normal rate law that we've been finding already. And if I give you concentration versus time, what immediately could you find from that? Say again? Integrated rate law. So it does depend on the data you have, on which one you'll find first, but once you know one, you already know the other. All right, this is really not the most important piece. It's just reminding you that data drives how you solve things. You can't solve anything if you don't have the right data for it. All right, thumbs up if that the connections are here. You're making connections to what we learned previously. Okay. Okay, so this is the bread and butter of today. I've got 3 slides like this: first order, second order, and 0 order. Take a minute, read and write, and then I'll explain. The stuff in purple is the newest, and then half-life as well. So keep writing. I'm just going to start explaining from the top here, okay? So we already know that a simple first order reaction, we have a reactant, and as its concentration changes, the rate of the reaction changes. So for example, if I double the concentration, the rate is going to be twice as fast because there's a single one exponent that's going to be affecting the rate. So for example, 2 times some exponent will equal rate. Well, 2 to the first exponent, meaning to the first order, will equal our rate times 2. So we already know this information. That's according to our differential rate law or table logic. So this is how we would write the rate law. We know that. But now we have a new equation that we involve time with. So now you can see t. Notice that t is capital or lowercase? Lowercase. That's how you differentiate between temperature, that's capital T, and time, which is lowercase t. So this is it. Natural log of concentration of reactant final is equal to negative kt, so time, plus the natural log of A initial. So not means initial, and F means final. So we are still looking over the course of time how concentration is changing, except we're modifying how we write the rate law to create a linear relationship. So do you guys see the linear regression line, like equation here? Do you see that? So where's y? First, right? So y is equal to mx plus b. Like that is the linear regression line. They always format, or I will always format it that way so you can still see where's the y-intercept. It should be at ln and initial. What's the slope? k. It's not negative k because k itself is not negative. The slope is just m, which is k, because the rate law constant itself will not be negative. It's just the correlation between us is a negative correlation. Okay, so if we plot ln of a, so this would be the which axis? Y-axis, okay? And then time, this would be the x-axis. Usually it's written the other way. So we plot it as ln versus time, ln and concentration versus time. We will get a linear slope, or a linear line, which will have a negative slope because of the correlation here. Okay, so we eventually will relate all of our integrated rate laws to half-life. Well, doesn't that make sense? Like, think back to honors camp when you guys talk about radioactive decay, like carbon-14. You said, okay, in this rock, you had like 100 grams of carbon-14, and 5,260 years later, you had half that amount. So you're looking at change in concentration over change in time, right? So that's all half-life is, so it's definitely related to our kinetics here. And so if you need a quick reminder, this is your definition of half-life. And then since we are talking about radioactive half-life is always a first order reaction. So everything that we've ever talked about is every half-life or every radioactive element scenario isotope we've ever dealt with has always been a first order reaction. Okay, so the next part is I'm going to back this up with calculus. Okay, some of you calculus people are like, yeah, okay, great. And then otherwise, I will tell you specifically what to write down. Okay, ready? Okay, so calculus people, do you guys recognize this? Yeah. Okay, so basically what we are suggesting is that all these different rates correlate to each other. They all relate. So the change in negative change in concentration over change in time, which is equal to the differential rate law, right? So these look familiar. We can integrate them with respect to time. So what we're doing is, what I have to tell you first is, there are a lot of like memorized integration rules, which I'm giving you the ones that apply, but there's hundreds of them. So what I'm telling you is that I've just rearranged this equation. So I took the T put up here, the A concentration down here. Now I'm integrating with respect to time from initial to final. And then as I take this, the rule for that, so change in x over x, the rule for that is equal to ln of x. You guys with me? I calculus people, everybody else just zone out for a minute, okay? So you now have just substituted in ln of a of final, and you're subtracting ln of a initial, and then as you integrate the k differential of t, it's just equal to kt. So then all I'm going to do now is rearrange this so it looks a little bit better. So I've distributed my negative out, so ln of a of final minus ln of a initial is equal to negative kt. And then what I have now, does this one look familiar? Yes, this looks like what we just wrote down. So remember, that is the first order integrated rate law. Okay, so that's what I would write down if you, I mean, you've already written it, but that's what I would put a star by. Also, draw your graph. So what have I graphed? What versus what? Change, or sorry, ln of A. So A is just my random general reactant. ln of A versus time has a linear relationship, but with a negative slope, so I'm drawing a straight line with a negative slope. And I'm hoping my R constant's like 0.999, right? So R squared should be 0.999. Okay, so this correlates to my Y equals mx plus b. And I've tried to put all this on the same slide here. So Y is the ln of A, M is our K constant, T is our time is our x-axis, and ln of A naught is our y-intercept. Okay? All right, so we know the equation, we know the graph. That's really what the most important pieces are. But if I have to solve for my own half-life equation, I should be able to do it based on the definition. What's the definition of half-life? One more time. Time it takes for half of the concentration so for the reaction to go down by half the concentration. Okay, so when I'm saying concentration final versus concentration initial, we can correlate those and say, okay, well, half-life is if I have a initial at the half-life, at the T1 half, which is what we'll call half-life, this should be half. So half of the initial. Okay. So T1 half, at T1 half, A concentration initial has just been divided by 2. Does this make sense? Okay, it's half of the original concentration. And since the final concentration, which is what I'm looking at the end of the half-life, is equivalent to this, I can plug that in into where I originally would have put our concentration final. This is still the integrated integrated rate law for first order. So when I plug that in, where I have AF, this is just going to be concentration change over 2, or sorry, concentration initial over 2. And then I just put a 1/2 here just to indicate like this is T 1/2, this is half-life time, but it's just time. Okay, so how do I solve for T 1/2 mathematically? How do I isolate that by itself? Subtract ln of A over 2. Oh, sorry, the other way. Okay, subtract ln of A naught. Divide by negative K. Okay. So subtract the y-intercept, and I have negative KT. And then I just switched all my signs because I didn't want to have to deal with the negative over here, so I just flipped all the signs just to make it easier for me. And then how do I mathematically pull two ln's together? What's the rule? There. Okay, so addition means, okay, it's actually subtraction, right? ln of A naught minus ln of A over 2. You divide them, right? So ln, logs and natural logs, when they're subtracted, you can pull them together as a division. You guys remember this? Algebra 2, remind me. Dang it, I don't need this here. Okay, so ln of like M minus ln of N. How do you pull those together if you're pulling the ln's as a single unit? Ln of M over N. Okay, if I had like ln of X plus ln of Y, how would I pull those together? Ln of XY. It's just I'm making a single unit. Okay, so that's what I'm gonna do here next. Well, okay. Actually, I did not do that next. I could not remember how I wanted to solve this. I think I just rearranged this first. And then I'm going to pull together those. Looks a little messy, but ln of A naught over 2. And I just put that over 1 so you can see the fraction over the fraction. Essentially, A naught over A naught are the same thing, so I cancel them out. So then as you divide by a fraction, it's multiplication by the inverse, so copy dot flop. Got it now? Okay. So it's essentially ln of 2 is equal to KT. So then I'm continuing to simplify, which is now dividing by K. This is the highlighted part. This is what you should write down if you don't write it down anything else. Okay. When you then divide by K, the half-life equation for a first order reaction. Okay, the half-life equation for a first order reaction is ln of 2 over K. So the T 1/2, which is the half-life equation, is ln of 2 over K. But nobody's going to remember what ln of 2 is. It's hard to do that in your head, right? So I'll tell you. ln of 2 is 0.693. So ln of 2 is 0.693 over K. Okay, so if you have nothing else in your paper, you have the first order integrated rate law with a natural log in it. You have a graph with a what slope? Negative, and you have the half-life equation. Yeah. You mean in the final half-life equation? It's because, so it's weird, and I actually have this right here next. What's weird about the half-life of a first order reaction is the half-life time is independent of the amount that you have. Okay, if you did not write that down, the half-life time, T 1/2, right, is independent of concentration. Look, concentration is not even involved in this equation at all. We went through all that work with concentration as it relates over the course of the time that it takes to react half of the reactant. But it doesn't even influence half-life. So the half-life is constant. So if I draw, I'll get your question in 1 second, Megan. So if I draw a radioactive half-life curve, which is what you've seen before, like who did Skittleium, right? Some of us did Skittleium in my class. You guys don't remember Skittles? The only time you could eat in the lab outside of ice cream? Okay. So if you took your initial concentration and you allowed it to go to half the concentration, that's the time it took, so that we're going to call that T 1/2. So I'm going to call that like 50 seconds. It took 50 seconds for some concentration to change by half. Well, it truly should stay constant because notice that half-life is not influenced by the concentration. So if I went another halfway down from there, and went over here, it's another 50 seconds. So this time would be what? 100 seconds. And if I went another half, it would be 150 seconds. So you'll notice that the half-life time is consistent. It's constant for a first-order integrated rate law. Question?
What does 2.5 represent? Like, is it just a way to say it's half-life?
It's just a way to designate half-life in a variable form.
So 2.5 does not represent anything.
Other than the time it takes for half the concentration to dissipate. Okay. All right. So that's first-order half-life. First-order integrated rate law. Next, second order. All right. New stuff is right here and right here. That's the new stuff for today. You want to write down where you came from. I'll speed my process a little bit more. I don't always show you the mathematical reasoning, but I think it's fun sometimes, so I like to prove you the math. Calculus people, does that make sense? Yeah. Tell Miss Hunter we did calculus already. You guys are taking the day off. So second order is 1 over the concentration. Notice there's no natural log involved. So 1 over the concentration final equals KT plus 1 over the concentration initial. What does this graph look like? What are the axes? 1 over, so the y-axis is 1 over concentration versus time, and what does the graph itself look like? Is it going down? Is there a negative slope? Positive. So there's no negative in front of the case. It's a positive slope. And if this is representing a linear relationship, there's no slope nature to it. It's a straight line. Okay, so r squared is 0.999, and it's a positive slope, which is the only one that's a positive slope in these 3 orders. So first order, second order, and 0 order, this is the only one with a positive slope. Most people forget that when we move on. So what we're going to do is we're going to derive this rate law once again. This is the integrated second order rate law. We're going to derive that quickly this time just to verify we can understand the pieces behind it. And then we'll do our half-life again. And then we'll do that last one for 0 order. So do you guys see this as a linear regression line? So what's y? 1 over a final. What's m? K. What's the x-axis? T, right? And then what's the y-intercept? 1 over a initial. Okay. All right, so we're going to go ahead and talk about the rest of this. All right, so I may not prove everything once again, but it does exist. There's a proof here. There's a proof here, because 1 over x, or x over x squared, the integration is negative 1 over x, which is why I have 1 over this now. So once I do all that, we get down to this. Do you recognize this now? This is the second order integrated rate law. Okay, so calculus backs it up. Now we're going to go to half-life. Okay, so how would I manipulate one of these variables to call it half-life? What would I do? T1 half, okay, so that's just indicating a final half-life. What else would I manipulate? I heard a final would be what? Would be what? Half of a initial, right? So a final is half of a initial because it's the time it took to get to half of the original amount. So I'm going to plug in a initial over 2 right there. All that we already said, positive slope, okay. Okay, so again, a final is equal to a initial over 2. So I'm going to plug this in right here. Looks kind of messy, but here we go. Scroll down all the way. Over here. Okay, so 1 over a final is 1 over 1, which I've now plugged in a initial over 2. So this looks messy, right? But how do you manipulate 2 fractions? Copy dot flop. So it's actually 2 over a initial is equal to kt plus 1 over a initial. Okay, so that's not too bad. I'm solving for t final, t1 half. So I'm going to then subtract on one side subtract on the other side, so it's 2 minus 1 is what? 1 over A initials equal to KT. Okay, so 1 over A initials equal to KT. And then how do I get T by itself? Divide by K. So then K just pops into the denominator, right? Because when you're dividing and you can just plug in the denominator, it's fine. So, highlighted thing is what you're writing down if you didn't write down anything else, okay? So T1/2, so the half-life of a second order reaction is calculated by finding 1 over K concentration initial. Half-life for a second order reaction, yeah.
So once you do all the math and find the numbers, you don't have to like divide by 2, but just T1.
Nope. It's just indicating like it's any indication, just indicate how that time is a separate instance from another time.
So it's just T.
It's just T, yeah. Okay, so now you'll notice that is this one dependent, is second order half-life dependent on concentration? Yes. Okay, so it's weird, we don't often see this, but for every secondary or tertiary or the next half-life, concentration goes from 1 to 0.5, your half-life is going to be, some T1/2 here. But as you continue to go down, what's happening to half-life? Is it getting longer or shorter? Say again? So is this number, so I went from like 1 as my initial concentration. Okay, so 1 over K times 1, that's 1 half-life. The next half-life would be starting with this 0.5, right? So how would putting 0.5 in right there change the time? Make it longer, right? It's twice as long. So it's weird. So you're dividing by a lower number, so essentially it's a higher time. It gets twice as long every single time you have a half-life. We don't ever see this. Like radioactive half-life is always first order, so we don't often see this. Okay? All right, last one was 0 order. The purple stuff is the new stuff. This one probably is more familiar. Normal stuff. So I've lined all these up to be a linear regression line. Y is equal to the mx plus b. But our axes are changing each time. So what's the axes here? What's the y-axis? Concentration. And then x-axis? Time. Where have you seen this before? No. Did you see this the first day we did notes on kinetics? Yes, right. We just have so far just only really been referencing concentration change over time, concentration change over time, concentration change over time. That's a 0 order reaction. It's when you're only considering how the concentration changes over time, that should have a linear relationship. What type of linear relationship for this case? A negative linear relationship. So this r squared is 0.999. And so basically that means that, you'll notice that here as well, does the concentration play a role in the rate? No, because this is just the rate law, or the rate law constant itself, the K constant. So the concentration, the rate is independent of concentration. That's what this is representing. There's a constant slope. So what is the slope, by the way? It's negative, but what is the slope in terms of the variables we have here? K, good. Slope is equal to K. And what some people will do is they'll try to go back and plug everything in this equation and manipulate, find K by itself and calculate K. No. Plug in stat plot, find the slope, you're done. It's just make sure that you put the right units on K, because you know K has different units for each order. Okay, so this one I wanted to give you an example. This one is usually one that requires a catalyst. So who's ever heard of a catalytic converter? Catalytic converter. Where would you have one of those? Come on, people. You know what? Cassie? Maybe in a nuclear plant? Anybody?
In the car engine.
In a car. Woo! Okay. So all of your cars have different, oh my gosh, make number. They're so young. Catalytic converters. Jeez, people. Who's ever changed their oil? Alright, who's ever seen their oil? Oh my gosh! Who's ever changed a tire? Who's ever seen a tire? Okay, thank you. Alright, so one day when your car breaks down, you're like, okay, I gotta find the oil, and it's the dipstick, right? You pull the stick out and you see how much oil you have left. Or do you guys just wait for the light to come on? Like, change your oil. Okay, well, anyway, so the catalytic converter takes harmful gases. It takes harmful emissions out of your, like, exhaust. Okay, so exhaust is bad. We don't want to breathe it in. It's bad. So it's going to take harmful emissions and convert it to good gases, good emissions that don't pollute the environment. Okay, so how do you think it's doing that? What do you think it's using to do that? Look at the phrase catalytic converter. What do you think it's doing? It's using a catalyst. All right, so catalytic converter. Let's say ammonia. This is just one that we would maybe see in our car engine or car exhaust, but it does exist. Takes ammonia, uses like platinum metal in a catalytic converter. The ammonia gases touch the platinum metal, and would this be a homogeneous or a heterogeneous mixture? Hetero, right? Because platinum is a solid metal. This is a gas, so that's hetero. It makes it makes nitrogen and hydrogen gas. Nitrogen gas, is that okay for our environment, guys? Say again, Megan? Like, that's totally fine for our atmosphere, right? That's fine. Is hydrogen gas okay for our atmosphere?
Yeah.
I mean, in small amounts, it'd be fine, right? So that's why these are better than. Is that right? Okay, good. All right, so technically those are better than ammonia or like carbon monoxide. Okay, it's the little things you learn in AP chemistry. Okay, so again, our rate laws as we indicated them earlier this week. I'm going to scroll down to where we actually integrated. Look, ooh, we integrated. Calculus people, thank you for appreciating this. Okay, and then here again, you see the what? Integrated rate law for what order? Zero order. I did go first, second, zero, okay? In this order anyway. And then I need to find, okay, so there's our y equals mx plus b. We've already achieved that. We got that on the first slide here. Now I need to find the half-life, right? So what am I plugging in for? What am I changing for my equation to find half-life? A naught stays the same. K is the same. T is just, I'm going to call it T1/2, but what do I call this? So A naught over 2. A naught over 2. So it's the time it took for half the concentration to change. Okay, so half-life is A naught over 2. So I plug that into the A final. So I have A naught over 2 is equal to negative KT plus A naught. I'm manipulating to find T. What do I do? Subtract A naught, okay? And then divide by negative T. And I'm showing you how to derive these yourself just in case you get in a pickle and you're like, oh no, I can't remember it. So what, right? You could find it yourself if you had to. It just take a little longer. All right, so here's your subtraction of A naught divided by negative K. So then T1/2 would be what we had final. And then I took this information and I manipulated it just a little bit more. Notice that this was, what's 1/2 minus 1? Negative 1/2, so negative 1/2 A over negative K. So I just basically took the negatives out and made it 1/2 of A over K. But since K is in the denominator, these two, the 2 and the K will actually just kind of come together as a denominator to make this right here the highlighted thing you're supposed to be writing down. So this is the half-life equation for a zero order reaction. Half-life equation for a zero order reaction. So what's weird is that the differential rate law has nothing to do with concentration, right? concentration does not influence the rate, but does it influence the half-life? It does, because it's in the half-life equation. So concentration initial must influence the half-life, because it is in the half-life equation. All right, so I want you to go back and look at the 3 half-life equations. You are memorizing those 3 half-life equations. Or does anybody have their if you have a reference table nearby, pull it out. Look on the lower left corner. Do you see the kinetics equations down there? All right, what does it only gives us a couple? What does it give us? Well, it gives us the ln1, which is the first order integrated rate law. It gives us the the second equation is the what? Second order integrated rate law, and the final equation is the half-life equation for first order only. That's why I say memorize them, because you'll still need to know the others. Okay. Okay. This is just an FYI. This stuff's useful in pharmacokinetics. What's pharmacokinetics? Pharmacokinetics. Half-life of drugs, right? Okay, so who's ever read the back of the bottle? It's like take once every 4 hours. Okay, why can you take it again after 4 hours? Supposedly the concentration has reacted to the point where it has, you've heated out and it's not going to be over-concentrated in your system. Okay, so yeah, it's definitely related to dosages of drugs and why we prescribe them at certain rates. I'm not going to show you that because I don't have time. Okay, so pull this out. I took a medicinal drug course. It was so cool, like so cool. It talked about all kinds of drugs and like anyway, so this is on that big sheet of paper. Yeah. Notice how is this data table different, guys? It's time, not rate. Thank you. Okay, whip out those calculators. List 1, list 2. List 1, list 2. Let's do list 1 as the x-axis. And if you're not sure how to plug this into list 1, list 2, or however it's deemed in your calculator, work with your neighbor. And you'll put concentration in the y-axis, and the y-axis is the only thing we will manipulate. Do not manipulate the x-axis. I should probably do this too. Calculator. Who does not have a calculator to work with right now? Give me like a beak. Does everybody have one? Because you absolutely need to do this with me. So you're clear. All right, so when you guys put this into L1 and L2, okay, just L1, L2, and you graph or you find the linear regression constant between time and concentration, what is the, sorry, let me back up. If I correlate, or I'm trying to correlate time and concentration, what am I trying to prove? Correlation between, or for what order? For which one? Zero order, right? So changing, so just time and concentration is zero order, right? So what's the correlation there when you run linreg here? Yeah, what's the R squared? 0.6? Ew, right? That's horrible. That's not even close to linear. So who got something like that? Okay, a majority rules, it looks like most of us did. I do have the answer someplace up here. Yeah, I got like 0.67, okay? So I'm going to go down to this graph right here. The first graph, I'm going to call it zero order. So the correlation between time and concentration looks like what? Is it linear, yay or nay? I think you have to turn diagnostics on if your R-squared value is not coming up, by the way. All right, so is it linear, yay or nay? No, so it kind of looks like this. R squared is like 0.67. No, that is not the relationship. This is not the most linear of the relationships. Okay. Thumbs up. Can I move on to the first order? All right. So at the top of your L1, can you apply a mathematical manipulation, and applies it to the rest of the data points? Right. So in the top of L1, in the top of L2, I want to now graph this data not as concentration, but as natural log of concentration. So how do I just put ln at the top of the list 1? ln of L2. If you put that in the top of your L2 list, that mathematical relationship should apply to the whole list. You do need to practice this because your calculators are essential. I don't know. Somebody help out. Second and number 2. Or you can just put ln in front of each data point. There's only like 5, so you're good. All right, I do want to make sure everyone knows how to use their calculators, okay? So if you guys make sure you help each other. Mine's different. So. All right, give me a thumbs up if you have your L2 in there correctly now. Some of it, okay, there's like 5 people have their L2 in there correctly. Is L2 in there as a natural log of all those data points of concentration? You good, Christian? Right, I want you guys to find the correlation constant for first order and second order, so I want to see that you guys are okay with that first.
Yes.
Well, then, okay, is this the first order? You need the R squared to show up. You need to try diagonal to space. Yep. Are you good? You need R squared to show up? No. We can try diagnostics on. How do you do that? That should work. Yeah, I'm just giving you a spreadsheet. So it's not straight. You guys don't have to pull up your own graph. You're just writing down that it's not straight. Like, don't get fancy on graphing. Can you get this in L?
What's the next one? What's the next
Okay, so eyes back up here for me. Time ln of concentration. What was the R squared value? 0.8 what? 5. Some change. Okay, so it's still negative. It's still negative, but it's a little bit straighter, but it's still not straight. It's just I'm just showing you how graphs could be given to you instead of the R squared values, but you're still seeing nonlinearity. So lastly, when you go back to the list 2, you're doing 1 over L2, right? So 1 over that gives you 1 over the concentration. So 1 over the concentration versus time. What's the R squared value? Point what? 0.9 what? 0.9 and some change. Okay, so definitely this is the most correlated or most linear relationship we have. So this was I know it didn't start at 0, but it's a positive slope. Just remember that's one was positive. So what we have to do is, given a set of data, okay, just like we just did here, given a set of data, you have to graph it 3 ways. So you have to run linear regression on the 3 different manipulations of concentration. Once you do all that, then you can claim through evidence, which is the most linear relationship, second order. Okay, so this reaction, whatever this reaction is a second order reaction. So now, from your stat plot data information, what was the slope? What was the slope of this last graph? Slope of the second order graph. 10.126. Is that what you said? Is somebody close to that? Or as long as we're close to 10, I'm good with that. So if the slope right here was 10.13 or something, that's supposed to be which variable? K, right? So y is equal to mx plus b. So 1 over the concentration. Final is equal to positive kt plus 1 over initial concentration. So K is M, slope is K. Okay? All right, so I already know the value of K, but what are the units of K, given the fact that it's a second order reaction? If this is K, molar seconds, good, over molar seconds, because it's a second order reaction. Okay, go back to your notes. What is the second order half-life equation? Say again, Megan. Okay, that is the second order, right? I mean, that was the first one we did. Okay, I think it was the last one we did. All right, so can you guys calculate T1/2 for me? Can you guys calculate T1/2? And I did not say, it did say on the half-life at the initial concentration, so what is the initial concentration? Right, 0.1000 molar. That's the one you have to plug in because that's how it was phrased. And then 0.100. What units cancel? Molar, and then you're dividing by a fraction, so what actually happens to seconds in the end goes back to the top, which makes sense. Time should be time, and that answer is 1 second, or point what? 0.9, I rounded, 0.988 seconds. So really, really short half-life, and it gets longer over the course of time. Okay, so given a set of data, what do I have to do to find the order integrated rate law? Graph them all, right? And then how do I choose? Most linear, right? So best R-squared value. And then from there, once you know the order, you can find K using it's just the slope, which you have in your data set, right, from your linear regression stat plot output. And then how would you find half-life? The memorized equation and plug in your slope is your K, and then whatever your initial data point given to you would be your initial concentration. Okay, we're going to do 3 problems in 20 minutes. That is my challenge to you. Specifically, let's go ahead and go down to the problem set, which is, I think it's called Wexton or something else. I'll put them on the board and work through them with you, and then we'll go from there. So I'm going to skip that one for now. If you can find this, it is in your, it's probably right behind the differential rate law problem set. It may not be exactly in order because I was looking for space on papers. You got it? Thank you. It is right underneath the complex problem set. Okay, we have to interpret data from a problem, not only from tables. Tables are easy because you just graph it all in all 3 ways and you move on. So this one's pretty easy though too, because what does it tell you up front? Hold on, at the very third word. It's a first order reaction. Boom, I don't have to graph a dang thing. It is a first order reaction. So once I know it's first order, I already know the rate law. What is the integrated rate law for a first order? I hear you, come on. ln of A initial, or A final is equal to negative KT plus ln A initial. Okay, so I'm just plugging A in because that's my generic reactant, but if I were actually given reactants, I'll plug the real deal in, okay? All right, so in the first order decomposition of cyclobutane at 750 Kelvin, it is found that 25% of sample is decomposed in 800 seconds. Okay, so, I'm sorry, 80 seconds. Does this matter? No, because it's a customary, it's a conventional way of always saying, here's the temperature of the reaction, and if I ever change the temperature of the reaction, the rate would change, right? But I'm just telling you that's just so you know that this is the temperature at which it's occurring. So, it doesn't matter, okay? So, it says 25% of sample has decomposed in 80 seconds. What is this? T, okay? So, I know T. The question is solve for rate law constant, so the K is my question. So, what else do I absolutely have to know? A initial and A final. So I don't know those, so I get to make them up. But I can make them up, I have to make them up with respect to the percent given. So if I'm never given an initial amount, I always just call it 1 molar. Keep it easy, right? So A initial, I'm going to call 1 molar. So then what's A final? Say again? 0.75. Don't question yourself. Yeah, it's 25% of the sample is decomposed. So if 25% is decomposed, you're left over with 0.75 molar. Okay, I have everything I need to achieve. Let's do this. I'm solving for the rate law constant. So can I manipulate this and solve for K? Can you guys do that with me? So ln, I'm going to try to write it here somewhat small. All right, so I want to solve for K, right? So what do I do to isolate K? Subtract ln of A, divide by negative T. Good, so I'm subtracting ln of A. So A final minus ln of A initial divided by negative T, that will equal to K. That's what you guys said. All right, now plug and check. We're good to go. Ln of, what do I plug in for A final? 0.75 molar minus ln of 1, right? A initial is 1. That is molar. Divided by negative 80 seconds. Plug that in your calculator. And you ready? Can you enter me in sundry notation? 3.6 times 10 to the negative third. I'm going to go with the sig figs I was given. So I was given, I just put in 1 and 0.75, right? How many sig figs was I actually given? 3, because it was 80.0 seconds. So let me record this to 3 sig figs, so it would be 3.0, or 3.60 times 10 to the negative third, is that what you guys said? Okay, so here's the problem. I know that I have molarity up here, and I know I have seconds, but I also know the K constants units for first order. What are they for first order? It's just per second, right? So this is K, and this is correct. But how do I cancel out these molarities up here? Divide, right? So do you guys remember LNs? When I subtract LNs, natural logs, what do I truly do? Yeah, this is actually ln of 0.75 molar divided by 1 molar. So technically, what happens to molarity? They cancel, and that's the problem. When we write it like this, it's hard to see the cancellation of molarity, but it truly does cancel because K in the first order cannot have a molarity in it. So if you don't remember that, just keep thinking how K should be expressed as first order. Okay, so then how do I find half-life of first order? So again, ln of 2 over K. So what is ln of 2? I told you to remember it. 0.693 over this, right? So 3.60 times 10 to the negative third per second. And then we all know what's going to happen in seconds to the end. They're going to what? They're going to travel to the top with me, yep. Ready when you are. 192. And that is seconds. Let's round that to 3 seconds. 193. seconds. Somebody knocking on my door. All right, thumbs up if you're done with this problem with me. All right. All right, let me choose a more difficult one. Let's go to 3. Give me, I'm good to go on, right? I got most of you guys saying thumbs up. How do you guys feel about this so far? I heard Taz say something, did not interpret what you said. Okay, so is this harder or easier than table logic? It's harder because there's equations, okay? Natural logs, but the equations are there and you plug stuff in, you're good to go. All right, so 3, the rate law constant for a second order reaction below is 48 liters per mole minute at a given temperature. How long will it take to decompose 90% of a 0.02 molar solution of nitrosyl bromide? Okay, start with what you know. Write down your givens. Anybody volunteer one thing they already know? Yeah, Darcy? Good, so that says the rate law constant, right? So you're interpreting that means K, and that's 48. It's weird, right? It says liters per mole minute. So what does liters per mole relate to if you write it in the denominator? Molarity, right? So it's liters per mole minute, but truly that's just 48 per molar minute, not seconds. I wasn't right seconds. Okay, so thank you, Darcy. Somebody else give me something else you know. Sweet. You know it's second order, right? So immediately you already wrote the integrated rate law, which is what? 1 over concentration final is equal to KT, so it's a positive one, good, plus 1 over A initial. And sometimes I just don't put, I just put brackets. It just makes it a little easier for me. Okay, so we know the second order reaction. How long will it take? What is this asking for, guys? It's asking for what? T. It's asking for time. Okay. Given what initial concentration? William? 0.020 molar. Okay. So how did you find the final? So if 90% of this decomposed, you're left with what? So you're left with 10%, right? And 10% of this is 0.1 times that, which would be 0.0020 molar. Okay. This was the only part I thought maybe we'd have a little bit of trouble with, finding the final. Give me a thumbs up if you're picking up what I'm putting down, taking the 90%, swiping that, leaving you at 10%, multiplying the initial by 10% to see how much was left. Okay, plug. I'm going to rearrange my equation first, just because that's how I roll. So T is equal to I'm ready when you are. 9, I heard 9, what? 375, thank you, minutes, because it's molarity over molarity. Molarities will cancel, leaving minutes on the very, very bottom, but it actually floats back up to the top when you divide. And that's going to be the how many sig figs? How many? 2 sig figs, so this would be what? 9.4 minutes. Alright, take a second to digest. Somebody just had their hand up. Emily, who else? What's up? You good? Okay. Once you know the order, you just plug it in. You just have to make sure you're interpreting the data in the question correctly. Alright, so try 5. Try 5. The 5 is on your paper right in front of you. I'm going to leave this up here for a minute for some folks to keep digesting first. Thank you for calculating quickly. I'm just making sure we're processing questions. So at this point, I think you're good to go, because you're just trucking through, it looks like. What did you guys call your initial concentration? 0.03, good, 0.03, because this is the first concentration they gave you. Yeah, it was after some time, but you don't have anything else to compare that to unless you call that initial. So then that was the first initial concentration given. So then what was the final concentration given? And that is supposed to be a capital M, sorry. That is final. And then, so what did you guys call T for time? 200 minutes, because from 200 minutes to 400 minutes, that was the overall last time. So initial to final, where there was a difference of time of 200 minutes. And then you're good to plug in.
eyes up here for just a hot second.
So give me a thumbs up if you were able to plug in and find K to be 2.03 times 10 to the negative third. And sometimes I write it as per minute, and other times I write it as minute to the negative 1 means the same thing, okay? Plugging into half-life equation, you got 341 minutes. And I did record 3 sig figs because of the information given above. Questions?
Why did you do 0.03 as your final?
So the way this was, oh no, I definitely been the wrong way on here. Sorry, I've already calculated. Oh, I took, so this is, I solved it as initial minus final. I negated the negative on my paper. So I solved it differently here. This is final, so that's 2, and this is initial, which is 0.3. When I did mine, I had negated the negative, so I did it early. But yes, thank you for catching that. The way it's written here should be final minus initial over negative t. But regardless, we got the k value. Okay, we got the t1/2 value. And so I got like a minute to show you the last piece. Who already kind of problem solved the last piece? Okay, some of us were figuring that out. So if the question's what's the initial concentration right here, I can't find that until I get to the ln of the initial concentration. So the way it was phrased at the beginning, it was like 200 seconds have passed and then you met 0.03 molar. So when you solve for ln of initial and you plug in for your final to be after 200 seconds, it was 0.03 molar. That was the 200 seconds that passed. That was the k value we had. You end up solving for ln initial to be negative 3.1. How do you offset a natural log? Say again? E, thank you, E. Okay, so what's the opposite of log? 10 caret, right? So 10 to the whatever. So the opposite of natural log is E. E to that will cancel out ln, and E to that will be what? 0.0447. So I'm going to round that. That concentration will be 0.0450 or 4470, something like this. We said 44. So. All right, so I will answer some more questions on integrated rate law. I will see you guys during intervention. My goal for intervention time is to do 2 things. To do your pre-lab for you have an pre-lab tomorrow. Okay, William, are you? So we have an inquiry lab tomorrow. The lab is really quite easy. Prep work, it takes 2 steps. So what we'll do is plus those 2 steps that you will knock out completely during intervention. That's my goal. If not, though, you guys will be finishing up in your own. So I have 2 things for homework. You see the problem set behind the lecture notes? 1 through 9. So 9 is for lab questions, and then 2 for Crystal Violet Lab. We'll tell you that during